So now let's think a little bit more about the motion of a particle in space, and let's relate it back to something we studied in the previous section, which was the Fresnel frame, or the TNB frame, right, with the unit tangent, unit normal, and unit binormal. Okay, well, if you remember, the binormal vector was constructed as r prime cross r double prime divided by the magnitude of that cross product, right, where r, of course, is the position function of the particle. Well, what that means is, well, r prime is velocity, r double prime is acceleration, so that means the binormal vector is perpendicular to both the velocity and the acceleration of a curve. Well, what that means is that the oscillating plane captures really well the motion of the curve at any given point. So it shouldn't be unexpected then that we can write, let's say, the acceleration of the curve in terms of the unit tangent and unit normal vectors. Right, remember, those are the two that make up the oscillating plane. Okay, so how can we see that? Well, so let's just write out here, r of t, this will be the position function, okay? And what is its unit tangent vector? Well, remember, that's simply r prime of t divided by the magnitude of r prime of t. Or in other words, that's the velocity of t divided by the magnitude of the velocity, which if you remember is just the speed, and we called that nu of t. So we already have a way to write the velocity in terms of these guys. So the velocity is just the speed times the unit tangent vector. Right? And that's maybe not too surprising, given the simplicity of t. Right? Well, how about acceleration? Well, how do we get acceleration? We take the derivative of velocity here. So a of t, which is v prime, right? So let's take this derivative here. So we're going to have to use the product rule on this. So it's the derivative of speed times t plus speed times t prime. All right. So t prime, that's almost the unit normal vector already. It's just missing the dividing by magnitude of t prime. Well, so how can we get that in there? That's what we'd really like to do. Well, the way we're going to get that in there is looking at what the magnitude of t prime is and somehow trying to come up with an expression that will involve n that we can eventually substitute back into here. Okay, well, remember that the curvature, kappa of t, remember that this can be thought of as the magnitude of t prime of t over the magnitude of r prime of t, right? Or, in other words, sorry, in other words, this is the magnitude of t prime over the speed. Okay? Well, we can use this and substitute this in to the equation for n. Right? So this is the guy in n. So let's go ahead and solve for that. Magnitude of t prime of t, that's just the curvature of t times the speed of t. Okay? Now we're going to use that and we're going to plug that into our expression for the normal unit normal vector. Okay? Remember, the unit normal vector, this is given by t prime of t over magnitude t prime of t Okay? We're going to go ahead and plug in this stuff down here now. So on the bottom we have the curvature times the velocity, and on top we have t prime of t. Well, t prime of t is the guy up here that we'd like to get rid of. So let's solve for it in here. Okay? So this is going to tell us t prime of t. This is just the curvature times the speed times n. Okay? So now we have a nice expression for t prime in terms of n. And now we're just going to substitute that back in up here for the acceleration into t prime, and then we'll have an expression of the acceleration in terms of t and n. Okay? So the acceleration of t, right, is nu prime of t times the unit tangent vector plus, well, we have nu times kappa nu n. So what we're going to get here is nu squared of t, kappa of t, n of t. And actually, I think it looks a little bit better if we do it like this. That way there's no confusion. It doesn't look like v compose v or something. Or nu compose nu, sorry. All right. So we've expressed the acceleration now of the curve in terms of t and n, as promised. Right? So what's the point of that? Well, that lets us talk about sort of the tangential and normal components of acceleration. Right? So this here, this is what we're going to call a sub t. Right? And this here is what we're going to call a sub n. All right? And what are the names of these? So this is the tangential component of acceleration. That's this guy here. And then over here, we're going to call this the normal component of acceleration. Right? And what that enables us to do is sort of in a nice shorthand way, write this as at times t plus an times n. Right? That lets us write the acceleration like this. And I've dropped the of t's here, but it's okay. All right? So these are going to be rather important things for us.